So today we're moving on to section 6.6, and we're actually going to get into those nuclear reactions that you probably thought about before we started talking about nuclear reactions. So a lot of people don't really know about nuclear decay. When they think about nuclear reactions, they might think of more along the lines of atomic bombs and things like that. So this will be our first introductory lesson into the ideas that go behind things like atomic bombs and things like nuclear reactors and things like that. So nuclear fission is the topic for today. Now, some heavy atoms, like uranium for example, they capture slow-moving neutrons. This process of capturing these neutrons splits the nucleus of the isotope into lighter elements and releases vast amounts of energy. So there is a ton of energy stored within mass that we're going to talk about today. And when these slow-moving neutrons approach a big heavy nucleus, like one that would be in uranium, that uranium nucleus captures that neutron, and because of the force of the collision, the nucleus would then split, and what we would get is lighter elements, so we would get some transmutation there, and then we'd also get other neutrons to go, which would form a chain reaction, which is what we'll talk about in the next lesson. So other neutrons are released from the reaction, providing opportunities for other big atoms to capture slow-moving neutrons and split and then send their neutrons off, which would collide and then split and then send their neutrons off, and it just keeps going and going, which is what a chain reaction is. So fission, the definition of fission is the process of splitting a heavy nucleus into two or more smaller nuclei, specifically with a neutron. So we're dealing with neutrons here going and running into nucleus. And then that nucleus will split into two or more smaller nuclei. Charged particles cannot be used for fission for two reasons. The first reason is because an alpha particle, for example, so remember that an alpha particle is a helium nucleus, which would be atomic mass of 4 and atomic number of 2, and because we have, and there's no electrons on here, because of those 2 protons, this will have a positive 2 charge. So if that positive 2 charge moves towards a nucleus, well, that nucleus, so for example a uranium nucleus, will have a charge of plus 92. Well, that nucleus is going to very strongly repel that helium nucleus, and therefore it will either get completely repelled, like pushed backwards, or else it just might get deflected. It'll just graze off of it. So that is the first reason, because of the charge of the nuclei themselves. And the second reason is because beta particles, so a beta particle which would be attracted, so remember that a beta particle is just an electron, right? An electron has a -1 charge. So if you bring that towards a positive 92 nucleus, yeah, there's going to be some attraction there. But since electrons are so tiny, they don't do anything. They'll just kind of run into the nucleus and nothing much will happen. Now, since neutrons are neutral, that takes care of the first problem. There is no charge, so there's no repulsion. And the second good thing about neutrons is that they're relatively heavy. They're at least on par with most of the particles inside, and therefore there is a chance to split things up. So they are the perfect particle for fission. The reason why neutrons must be slow-moving is because it increases the chances of a successful collision. Tough word to say sometimes. If the neutron is moving too quickly, then the chances of a successful collision go down quite a bit. So if it's moving slowly, then we just have a better chance of fission happening. Now, a lot of times neutrons are moving too fast for fission to occur. So we bring these things in called moderators. Guys, we bring these things in called moderators, and moderators are basically substances with low atomic masses that slow neutrons without absorbing them. So, for example, like good moderators are things like water. Water is a molecule that is very small compared to something like uranium. So what it does is it runs into the neutrons, it slows them down, but it doesn't break the nucleus up. It's too small. Heavy water, for example, is another one. Beryllium or graphite. Graphite's just another form of carbon. So, for the record, water is H2O. I think that we all know that. But some of us might not know what heavy water is. The hydrogen that's part of water is normal hydrogen with an atomic number of 1 and an atomic mass of 1, which means that it's composed of a proton inside of its nucleus, no neutrons at all. Heavy water is still H2O, because that technically is the chemical compound for water, or formula for water. But the hydrogen here is deuterium. So deuterium is an isotope of hydrogen. It has atomic mass of 2 and an atomic number of 1, which means it's made up of 1 proton and 1 neutron within the nucleus. So it's basically double the mass of a normal hydrogen. And because it's double the mass, we just call this heavy water because it's slightly heavier than normal water. Not much heavier, but just slightly. And we will talk more about heavy water when we get to nuclear reactors. So again, moderators, they just slow neutrons down so that fission can become possible. The neutrons produced by fission travel quickly unless they are moderated. So when the neutrons from a fission reaction get expelled, they get expelled at very, very high speeds because of the massive amount of energy that gets produced. So we need these moderators there in order for more fission to happen. So here's a typical fission reaction. What we have is our uranium nucleus right here, and we have a slow neutron moving towards this uranium nucleus. After the uranium nucleus gets hit, what happens is we get a lighter element, krypton in this example, gets shot out one way. We get barium, another lighter element, gets shot out the other way. And then we also get these neutrons that get expelled out as well. Now these neutrons would theoretically, as long as they get moderated, would become another slow neutron for another uranium atom, and then more fission would happen. So like I said, it turns into a chain reaction. So this is what a typical fission reaction would look like. You've got your uranium-235, atomic mass of 92, reacting with 1 neutron. So remember that the symbol for neutron is atomic mass of 1, atomic number of 0. After that, what we get are these two elements. Krypton, which I feel like it says krypton 90, but it's kind of blurry on my smartboard. Can you guys see what that number is? Is it 90 though? Like that? And then the other one is barium. And it's barium 144. And, well, let's check it because it's going to be the same on the periodic table. Oh, KR is 36. Sorry, guys. Let's just wait a second. So this will be 36. What's barium? Yeah. 56. Okay. And then in this particular reaction, because we get these other 2 neutrons happening, I think it's 144. Okay, so then we also get 2 neutrons, so 2 neutrons. And then the last thing, and I ran out of room in this linear line here, but the last thing that you can add if you have room is energy. And a lot of it. So even though that atoms are very tiny, they give off vast amounts of energy when fission occurs. Now, I guess a lot of energy compared to their size, because we think that atoms are atoms are very, very small. But the amount of energy that is given off in situations like this is really big. It's actually kind of surprising. So if you have a whole bunch of uranium nuclei together, call that an atomic bomb. And when 1 neutron gets thrown in there, and causes a chain reaction with all of these other uraniums, and each uranium is giving off vast amounts of energy, that's when we get huge explosions, huge energy released. So we'll explore this concept a little bit when we get to the questions that I'd like you to do. Now, any chemical reaction either absorbs or releases energy. And this is the same for nuclear reactions. However, we tend to stick to those that release energy because the amount that is released is so enormous. And usually we can use that energy in some way, whether it is, unfortunately, for destruction purposes, like an atomic bomb, unfortunately, or whether it's for practical uses, like using that energy to power our homes, like in a nuclear reactor. That energy can be very, very useful. In 1905, Albert Einstein published his theory of relativity that basically reshaped modern physics. 1905 was a groundbreaking year because for hundreds of years, we were on kind of a one-track mind in terms of physics. And that was Newtonian physics, so dealing with, infinite speeds, and so on. When Albert Einstein came around, he said things like, there is a speed limit, and it's the speed of light. Nothing can approach the speed of light, which completely went in the face of what Newton was saying. Newton said you could theoretically increase your speed to whatever you want it to be. And then Einstein came along and said, no, you can't. Because it would cause, you would need an infinite amount of energy in order to accelerate something that fast. Which is kind of a mind-boggling concept. So he kind of made the world of physics kind of open up their eyes and say, hey, there's a lot going on at the atomic level, so let's kind of start to explore this. So in his document that was dealing with the theory of relativity, he suggested that mass was another form of energy. And therefore, if a decrease in mass for a system is observed, it might show up as an increase in energy. And the relationship that he found between mass and energy is that very famous formula that you all knew before walking into this class, which is E equals mc squared. What you might not have known are what these letters stand for. The capital E stands for energy, and that energy is measured in joules. The M stands for mass in kilograms, and the C stands for the speed of light, which is 3 times 10 to the 8 meters per second. Now, what this equation says is that energy and mass, guys, energy and mass are the exact same thing, they're just in different forms. So if you can imagine potential and kinetic energy, remember that when we said when we raise something above the ground, we give a potential energy. When we let it fall, that potential energy is converted into kinetic energy as the speed increases. So kinetic and potential energy are the same thing, they're just in different forms of one another. So he said, if they are the same things, then we should be able to convert mass into energy, we should be able to convert energy into mass. That was his theory. So then he started to think about this and started trying to find out ways to find this out. So the decrease in mass between a parent nuclei and the products of fission is equal to this energy that's created by that is equal to the energy that's created by this product. So I just want to go back to this equation that we wrote down right here. I'll try to use a different color here so this kind of makes sense. If you were to take these three things and add them all together, so sum them all up, what you would find is that there's something missing. The sum of all of these nuclei together on a scale would be less than the sum of these. These would be heavier than these. And when you think about conservation of mass, so if you've taken chemistry, we always said that mass can never be created nor destroyed, right? So if you have 2 hydrogens on the left-hand side of your equations, you have 2 hydrogens on the right-hand side of your equations. So when we start to measure the masses of the products in a nuclear reaction versus the mass of the reactants in a nuclear reaction, we find that they don't equal. And that flies in the face of everything that we've ever talked about in chemistry. The key here is that this missing mass is converted to energy. And this process of converting mass to energy unleashes unimaginable amounts of energy, which is where you get your atomic bombs, which is where you get your nuclear reactors that power our homes. And that was a wild concept in the day. Is this relevant? Yeah, we're talking about splitting the atom here. Yep. We will talk about the amount of energy given off once we get to some of the problems here, and once we get to some of the problems in the notes and some of the problems that we'll go through in the textbook. So here's Einstein's equation. Now, since this energy originates from the conversion, so again, we're still talking about this missing mass, right? Since this energy that is created in our fission originates from the conversion of nuclear mass to energy, we call this nuclear energy. Okay, this energy that's being produced is called nuclear energy because it's coming from the nucleus of an atom. So this is stored in the a stored energy. So when you have an atom and you've got particles inside that atom like neutrons and protons, there's a certain amount of energy within that atom. We call it stored energy or potential energy. So it's just like holding a textbook 2 meters off the ground. There's some stored energy in there. It is not useful until you let the book go, and then you can use that energy. So just to do a calculation involving Einstein's equation, I just want to do this example here. So it says a nuclear reaction produces 9 times 10 to the 11 joules of heat energy because of the conversion of mass into energy. I just want to know how much mass would be needed in order to make this much energy. So remember that a joule is a very, very small unit. However, we've been dealing with joules a lot in physics. So if you remember back in like physics 20, you talk about thermodynamics, Q equals mc squared. Q is joules, Q is energy. We had some pretty high energy values. Okay, but we also had decent amount of masses. So we'll compare, what you can do is kind of compare the amount of mass needed for this to happen and the amount of heat that's transferred in thermodynamics. So the equation here is E equals mc squared. So the amount of energy that's unleashed here is 9 times 10 to the 11 joules. So 9 times 10 to the 12 would be 9 trillion joules. So we're dealing with 900 billion joules here, a ton of energy. We're looking for the mass that's required to give us this much energy, and the speed of light, which, by the way, if you don't know off the top of your head, should be at the bottom of the formula sheet right here. 3 times 10 to the 8. So we need to take our 3 times 10 to the 8 meters per second, and then we need to square that. And after you square it, then you need to divide it over to the other side. So 9 times 10 to the 11 divided by 3 times 10 to the 8 squared is 1.0 times 10 to the negative 5 kilograms. If you want that in a bit like a different form, not scientific notation, it'd be 0. kilograms. And if we think about that in terms of grams, then I'm just going to move this decimal 3 places to the right. No, it doesn't matter what's the answer is going to come out to kilograms. I'm trying to make this into some comprehensible numbers here. So 0.01 of a gram. So we're talking about 100th of a gram to give us 900 billion joules of energy. That's not very much mass, and that is an unbelievable amount of energy. Now that being said, it's really difficult to perfectly convert mass into energy. But you would have a total amount of mass from a certain reaction. So you'd have probably a whole bunch of reactions, and only this much mass has been converted into energy. You're not just going to ever take 0.01 grams, put it into like a nuclear reactor and get, this much energy put out, because machines aren't that efficient, and neither are some chemical reactions. So, or some nuclear reactions, you need a lot of these fission reactions to happen in order for this much energy to get produced. But I really hope that we're kind of grasping how little mass we need to get a lot of energy. Now, one other part of nuclear physics, at least a pretty relevant unit, is something called the electron volt. So the electron volt is equal to the energy that an electron has when it is accelerated by 1 volt from rest. So if I have an electron sitting here, it's just sitting there on an atom, and I connect a current, like I connect electricity to this, of 1 volt, then that 1 volt will give this electron energy, and it will start to move. So the amount of energy that an electron gains from that 1 volt is called an electron volt. Now 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So not very much. Okay, so there are going to be some questions out there where electron volts are talked about. So I want to be able to convert electron volts into joules, and from joules to electron volts. So I just want to do a couple more examples here. This question says, how many electron volts of energy are converted from the following masses in a nuclear reaction? So you get a bunch of nuclear reactions happening, and in the end, you have changed 2 kilograms of mass into pure energy. So in order to find out the amount of energy that you get from this, you're just going to use E equals mc squared. The energy from 2 kilograms of mass times by the speed of light squared. So you should get a huge number here. So let's go to 3 sig figs, so 1.80 times 10 to the 17. Now this will be in joules. Now the question says how many electron volts. So this is going to go back to dimensional analysis. So what I'm going to do is I'm going to take this amount of joules, 1.8 times 10 to the 17 joules, and I'm going to multiply by this. 1 electron volt per 1.6 times 10 to the negative 19 joules. So 1 electron volt per 1.6 times 10 to the negative 19 joules. Basically what I'm doing here is I'm dividing, because when I multiply this off, my joules will get to cancel off, and I'll be left with electron volts. I got that from right here, and just for the record, that number is on our formula sheet as well, I'm pretty sure. Just double check. Yeah, 1 electron volt is right there. 1 times 1.0 times, sorry, 1.60 times 10 to the negative 19. So BT, if you guys could let me know what I get for my energy value in electron volts, that would be great. Guys, do you have an answer for me or not? Sorry, I didn't hear you guys. Brandon, do you want to help me out here? No, we should have a very, very big number. So remember that we're dividing here, right? So 1.13 times 10 to the 36 electron volts is what we should be getting. So just for the record, I knew that it was going to be a big number because I am dividing by a very, 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 very small number. So when you guys did that, there's two types of people out there. There are people that refuse to use the exponent button on your calculator. There's an EE button or an EXP button, or yeah, that's usually what they're called, either EE or EXP button. There might be like a times 10 to the X button. If you use that button, then it takes whatever you put in as a single number and not a bunch of operations like times 10 to the. So if you do not like using that button, then you need to be a brackets person. So those of you that got the 0.00 number, I need you to go 1.8 times 10 to the 17 divided by bracket 1.6 times 10 to the negative 19, close bracket, and then press equals. And that is what you should probably be getting you to 1.13. So we will try that again. Let's try this 0.1 milligrams. Now, just for the record, milli means I need to move it 3 places to the left. So I'm going to have 0.0001 kilograms. That'll change this to kilograms. So E equals mc squared is equal to 0.0001 kilograms times by 3 times 10 to the 8 squared. Nope, milli actually means thousandth. Micro means millionth. Remember, micro is 6 places, milli is only 3. Yep. Nine times 10 to the 12. Okay, so that'll be 9.00 12, and this will be joules. All right, so now, sorry, I'm just going to separate those two questions. Now, for me to get electron volts, I need to take my 9 times 10 to the 12 joules and multiply by or divide by and this should give me my electron volts. Electron volts. So I need kids in Beachy, Brandon, I need you guys to double check these answers please for me. Let me know if that's what you got. Thumbs up will suffice. Okay. Again, if you're not an EE person or EXP button person, then you need to be a brackets person. All right. Thank you very much. Now, one interesting thing about a nuclear reaction is that mass is not conserved. Okay. In fact, if you added up the individual mass of the protons and the neutrons for a nucleus and compare it to the neutron's actual mass, you'll find that there is some missing mass. You'll find that So for example, let's talk about carbon-12. So carbon-12 is made up of 6 protons and 6 neutrons. If you added these protons and neutrons up, they will not equal the mass of your carbon-12 atom. The mass of your carbon-12 atom will actually be slightly lighter than the total sum of these protons and neutrons. And that doesn't make any sense at all. If I take some protons and neutrons and put them together, why are they not the exact same? It's like saying I take a 100 kilogram mass, put it with another 100 kilogram mass, and I get 199 kilograms. Doesn't make any sense. So what we say there is that the mass of the parent nuclei is greater than the sum of the protons and the neutrons together. And we call this discrepancy the mass defect. We recognize that there's a defect with the sum of the parent nuclei versus the sum of the individual components of that nuclei. So I've got an equation here for you. MD I call the mass defect. The mass defect is equal to the mass of the nucleus minus the mass of the neutrons and the protons. Now I gotta tell you that this equation can be extremely confusing because I've got two n's in here. So what you might want to do is call this MD. You can even write this on your formula sheet if you want. And I apologize because this is an equation that I kind of am giving you. But call it mass of the nucleus minus mass of the neutrons and protons. At least there you're not getting the two n's confused. We know that one is for the nucleus and one is for the neutrons. So please add that to your formula sheet or change it on your formula sheet. I don't want any confusion here. Now, one of the reasons why there's this mass defect is because of how the nucleus is bonded together. So, for example, for my 6 protons that make up my carbon nucleus, and then there's all these neutrons in here as well. I'm not saying that they're all bonded like that, but there's 6 protons, 6 neutrons. All of those positive charges are trying to get away from one another. Yet they're not. They're staying stationary. It takes energy to keep those things together. Imagine taking 2 magnets and the opposite, or having the same poles, try to push them together. You can feel the repulsion happening. Protons feel that all the time because they want to get away from one another. Yet there's something in there that's gluing them together, and that's energy. And therefore, what happened is a little bit of the mass that's inside of the nucleus has been converted to energy. It's been sacrificed to make those protons stick together. We call that the binding energy. So the energy required to keep a nucleus intact, to overcome the positive charges that are inside of the nucleus, is called the binding energy. And this value is going to be negative. Protons and neutrons are typically measured in atomic mass units, also called AMUs, or sometimes just U. So that is like, so instead of calling it kilograms, we're going to call it atomic mass units, AMUs, or just U's. Now we typically say that a neutron and a proton are both exactly 1 AMU in general conversation. However, that's not 100% true. In fact, the mass of a proton is 1.007825 atomic mass units. And a neutron is 1.008665 U's, or atomic mass units. So a proton is basically 1,000th of a AMU greater than a proton. Now 1 AMU is equal to that many kilograms, so, oh man, not very much at all. 1.6605 times 10 to the negative 27. All of these values, by the way, are given to you on your formula sheet. By the way, if the bell goes before this lesson is done, we will finish it up on Monday. So I just want to keep going a little bit here. we can use these values to calculate this mass defect, okay? And then we can use Einstein's equation to find out the binding energy. So basically what we're going to do is we're going to calculate the mass defect. And remember that the mass defect is the missing mass. That missing mass has been converted into energy, which we can use Einstein's equation to find. So the mass of a radioactive isotope tritium, which is hydrogen with 1 proton and 2 neutrons, is 3.016049 atomic mass units. I want to calculate the mass defect. So my equation for the mass defect was equal to the mass of the nucleus minus the mass of the protons plus the neutrons, or neutrons plus protons, doesn't really matter. Now the one thing that you're going to want to say here is that there is 1 proton. So remember that that's what that number is right there. The bottom number is the number of protons. The number of neutrons is the atomic mass minus the atomic number. So 3 minus 1 is 2 neutrons. So my mass defect here is going to equal the mass of my nucleus, which is 3.01, oops, yeah, 60, yeah, what's up? Electrons for neutral isotopes is always equal to the number of protons. So the mass of our nucleus of tritium is 3.016049 units, or atomic mass units. I'm going to subtract the sum of my protons plus my neutrons. Well, I have 1 proton, and the sum of, or the atomic mass unit for a proton is 1.007825. And I also have 2 neutrons, and each neutron is 1.008665 units, or atomic mass units. Okay, so I know that we have a lot of decimal places here, but the math here is unbelievably simple. So we're just going to basically, I want to break this up a little bit because we have so many decimal places. I just want to know what my brackets are. Okay. So my brackets are 3.025155, and the mass defect is, what is it? Oh, is that what you got? Sorry. Okay. So now when we subtract this, we're going to get negative 0.008665 units. Now on the test and on the quizzes, I'm going to ask you to go to 4 sig figs, because I want us to have quite a bit of accuracy here and quite a bit of precision. So that is a fine answer to have. Either units or AMUs. So either U for unit or AMU for atomic mass unit. It's just a U. It doesn't have to be as fancy as that one. It's just... We actually should be able to finish this up. We've got a couple minutes here, and then we'll do the questions on Monday. To find out the binding energy of this isotope, what I want to use is E equals mc squared. The problem here is that I need my mass to be in kilograms. Now what I need to pull in here is this number right here, which is on your formula sheet. 1 atomic mass unit is equal to 1.6605 times 10 to the negative 27. So if I have negative 0.008665 AMUs, I'm going to multiply by per 1 AMU, I'm going to have 1.6605 times 10 to the negative 27. kilograms. And what we'll get there, so now we're just going to multiply. You should not have any problems with brackets or anything in this particular case, because you're not dividing. No, it's going to be negative. Yep. Let's go to 4 sig figs. And this will be kilograms. Now I want that negative because it is a mass defect. The negative tells us that something is wrong. I have a discrepancy between the components of my nucleus and the sum of the nucleus itself. So just to calculate the last thing here, we just need to bring that kilograms into our Einstein's equation, E equals mc squared. So 3 times 10 to the 8 squared multiplied by negative 1.439 to the negative 29. I got negative, sorry to rush this here, negative 1.295 times 10 to the negative 12. And now this answer is going to be joules. So that is what we call the binding energy of our nucleus. So that's how much energy was released. So not a whole bunch when you're actually creating atoms. We get the lots of the energy. Now this is a negative energy because it was energy lost. Because it was lost. It's missing mass. And it's always negative because of this mass defect. And those are the questions that I'd like to do.